Hello, everybody. I don't think I have to introduce you.
But in any case, he's going to talk about, I think, 3 different things. And well, as you can see, the title of the talk is Relaxation Processes near massive black holes, which embraces all these 3 things.
Okay, thank you very much. So good morning. I apologize for disrupting the program by foolishly believing in airlines. Never will happen again. So this talk is a modified version of the talk I gave in Barcelona just a while ago. Some things are new, and in others I hope I have more time this round to explain things a little bit more detail. But since this is a very informal meeting, and since some of you were in Barcelona, if you feel that I'm maybe over-explaining things you know, just give a polite hint or interrupt me. Okay. That's the spirit. Okay, so the first thing I want to emphasize, and I guess it should be pretty obvious to this audience, is that the great challenge of detecting and interpreting gravitational waves is actually coupled very strongly to a stellar dynamics challenge. And one of the questions where this linkage is strongest is the question of MBHs. And this raises the question, a legitimate one from the gravitational wave community: why have we been dynamicists so late in realizing this? And the answer is simple. The level of detail that is required to correctly predict, say, the rates and orbital properties of MBHs, which of course are reflected then in the detection probability and in the waveform signal, is such that the level of detail that is required is so high that we have never really needed it until this point. And one example, which as far as I can tell, was in fact the only time that we were really interested in the way things behave as they fall into a black hole, was before gravitational waves, was the question of feeding black holes by the accretion of star mass and the resulting accretion flares, which were at a certain point thought to be promising a way to detect the existence of black holes in galaxies. Now, in the question of feeding a black hole, you're really interested only on the long-term statistics of the rate on cosmological timescales. You don't really care about individual events. And as far as the accretion flares are concerned, you give up ahead of trying any chances of actually predicting in very great detail how an individual accretion event will look like. We know that accretion is an extremely challenging problem, which is tied on many different scales to questions of the microphysics of gaseous processes. We know we have a hard time dealing with it even in local galactic accreting objects, and it's obvious that if we would have tried to predict what will happen on cosmological scales, we would probably fail. And so this issue of what happens to stars and compact objects that approach a black hole actually did not require an answer, and there was no great need to answer it in any great detail until prospects of gravitational wave detection became real. And so what happened was that once people started looking in much greater detail into the dynamics of this process, it turned out that there were many, many new features that at this level of detail become very relevant. And the outcome is that today I think there are many more questions than answers about how these things actually work. This is, I think, a fascinating time in terms of the stellar dynamics aspect of this problem. And we're learning a lot of many things at a very rapid rate. And I will first spend some time giving you some general statements about the problem, which I think are also non-trivial, and then discuss 3 different types of relaxation processes which are closely related. We heard yesterday already about strong mass segregation. It's I put it here in the end. I don't I'm not sure that I'll get to it, and if I would do, I will not spend too much time with it because I think you got the main picture yesterday. And I'll mention first relaxation, massive perturbers, and each of these embodies a different combination of coherent or non-coherent kinds of relaxation, and whether it involves many body, few body, or two body processes. And this is just, there's no guarantee that this is the full list. It may well be that there are other, even less obvious processes that are important, and we simply haven't yet stumbled upon them. So, in my mind at least, it's quite clear that Lisa will be telling us many important things about the dynamics near a massive black hole, fundamental things about the statistical mechanics of such systems. So, first of all, one of the important things to realize is by pure coincidence, Lisa will be selecting out of the sky a very special subset of all galactic nuclei, those that are dynamically relaxed by two-body relaxation mechanism. That is the slowest and the inherent kind of relaxation process that we have in any two-body system. Any discrete n-body system. And this is an outcome of an empirical fact about the connection between the mass of a black hole and the velocity dispersion of the spheroid that hosts it. So in the case of a spiral galaxy, the spheroid is the bulge. If we're talking about the elliptical galaxy, then the entire galaxy is considered to be the spheroid. And there are many different ideas why this relation exists. Roughly, the mass of the black hole scales like the fourth or maybe fifth power of the velocity dispersion, defined with some appropriately large radius. We don't really know why that is, but it's a very strong correlation. It's probably telling us something very fundamental about the connections between the formation of the galaxy and the formation of the black hole. But we don't really need to understand it just to realize what the implications are. So a key concept is to define for each of these galaxies is the radius of influence, which conventionally can be defined as the radius where the potential of the black hole starts to compete, or the potential of the stars, self-gravity of the stars competes with the potential of the black hole. So if this sigma squared velocity dispersion is the asymptotic velocity dispersion very far from the black hole, assuming that one can actually define such a distance-independent velocity dispersion, then an order of magnitude estimate of the radius of influence is given by this, and if you plug in this scale relation, you get that it scales like the square root of the mass of the black hole. Now, the quantity that will be useful to consider is the mean stellar density at RH. Now, another way of defining, or it actually comes out from the Viral theorem, that if you define the radius of influence this way, it also means that roughly within the sphere enclosed by the radius of influence, you have a mass in stars which is the same order as the mass of the black hole, and so you can easily estimate that the mean stellar density averaged over that volume scales like 1 over the square root of the mass of the black hole. Now, the relaxation rate, which is 1 over the relaxation time, can be derived up to correction factors by a simple NV sigma kind of cross-section collisional rate. So here we have the density times the typical velocity times the typical distance squared, and the distance here is the distance where collisions start becoming strong. That is, the deflection between two stars is of the order of a radian in the change of the velocity factor. If you plug in all the relations above, you find that the relaxation rate scales like this. And for future reference, let's remember that the relaxation rate actually depends on the mean density times the stellar mass squared. And that squared is going to play a role later when I discuss massive perturbers. But for now, we can then just plug in all the prefactors that include the physical units and do the calculation just a little bit more rigorously. And we find that, for example, if you plug in values relevant for the black hole in our galaxy, which has a mass of 4 million solar masses, the relaxation time is roughly of order of 1 gigayear, perhaps a few gigayear, And in any case, it's substantially shorter than the age of the universe, which is also taken to be the age of the Milky Way itself. And the density, even when averaged over the radius of influence, which comes out to be a few parsecs for our galaxy, is already a very high density. For calibration, this density is like the core density of a very dense global cluster. And that's only at the edge of the region. As we will see, the density profile that one expects to have is a power law, which means that it grows very steeply as you go close to the black hole, to fractions of a parsec from the black hole, and then you reach densities that are as high as 10 to the 8, 10 to the 9 stars per cubic parsec. That's as large as 10 orders of magnitude more dense than in the solar neighborhood, and very different types of stellar processes, dynamical processes, start occurring when you reach such high densities. Now, by this scaling, you see that if we were to consider, say, a black hole that is a few times larger than the mass of our black hole, the typical scale will already exceed the age of the universe. So that means that black holes up to, say, 10 to the 7 solar masses are expected to have relaxed cusps, relaxed stellar systems around them, but beyond that, the systems are not expected to be relaxed. And by sheer coincidence, that coincides with the sensitivity range of LISA. And as far as I know, this is a pure coincidence. But it also means that it has several important implications. So first of all, we know, for example, we could worry what happened to the galaxy if it has undergone one of these major mergers where two big black holes merge. And this relation tells us that if the mass of the black hole is low enough, we can expect that over a fraction of the age of the universe, it would be returned to its equilibrium. So this means that our predictive power is much better, of course, since we don't have to know the history of individual galaxies to guess at what are the dynamical conditions around them. And this also tells us that if two-body relaxation already dominates the dynamics, even in the absence of any other more fancy, so to speak, process, then we can more or less disregard the first guess long-term secular processes, which could be very, how should I put it, complicated or depend sensitively on initial conditions, on the setup of the galaxy, and concentrate simply on looking at processes that are even faster than two-body scattering. Yes?
Your argument, mostly the relation has been established on massive systems.
Right.
So by your argument, you're unrelaxed. Would that mean that...
No, not quite. I mean, they do go down to about 10 to the 6 solar masses.
A few of them. So could it be that for the nuclei that Lisa will look at, relaxation change the relation at something?
It could be. I'm not so worried about masses that approach 10 to the 7 because I think that there are a substantial number of data points on that range. But I agree with you that extrapolating it towards 10 to the 6 and even beyond to 10 to the 5 is highly speculative. That's a good point. Okay, so just very briefly, I'd like to make the point that having a high density cusp comes with many, many different and very fascinating and physically rich phenomena that can be used to test any ideas, theoretical ideas that we have about what happens in systems that will be LISA candidates. And that's completely independent of LISA or any of the considerations that go into the gravitational wave physics. And I believe Melvin will be talking about some of the items that come here. You can see I put here a totally incomplete list of references for the many different types of kinds of interactions. Some of them can be observed only or tested in any significant way only in the Galactic Center because you really need to look at stars from up close. Others have cosmological implications. I won't go through the list. The point I want to make here is simply that we can make progress and test our ideas with the data coming from non-gravitational or non-gravitational wave channels. And I think that the possibility for synergy or crosstalk between these different domains is a very important one, and we should all keep it in mind. But the subject of today is relaxation processes as they relate to gravitational wave physics. And I think that Clovis may have talked about this. Did you, Clovis? So I'll just do this very, very briefly. Clovis already told you that to get to the black hole, the faster way is to relax angular momentum than to relax energy. That's expressed up here. And then, in the absence of any kind of dissipational mechanism, if you plot your phase space in terms of angular momentum and energy, and I'm using here the usual convention that the energy is defined with a minus sign, so high positive values mean that we're very close to the black hole. And so you have a region, the red region is where no stable orbits exist. It's either when you're beyond the last circular stable orbit, or if you are on a very radial trajectory with an almost zero angular momentum. The star can survive if it's here. This diagonal line expresses the fact that at any given energy you can only have up to some maximal angular momentum of the circular orbit. And as long as you're far away from the edges, both in energy and angular momentum, you basically get kicked around randomly by interactions, two-body interactions with other stars, at a rate which is quite similar in both directions. And this is because this prefactor here is very close to unity, so roughly the angular momentum, the time scale to change the angular momentum by order of itself is the same as that of the energy. On a logarithmic scale, that simply means that at a given time, so if you imagine, say, that every zigzag here represents a change over some fixed unit of time, say 1,000,000 years or 1,000,000,000 years, you travel this way the same as that way, and you just keep getting diffusing in the phase space. But once you are by random kicked into a low angular momentum position, the rate at which you change in this direction is much larger than in this direction. So to some approximation, you can then think of your movement in phase space as lying on one dimension, on one direction, this direction, and if you wait long enough, you will be thrown into a lost cone orbit and fall into the black hole. This is what we call a plunge. Now, this was the main process that was discussed 30 or so years ago when people were worried or thinking about what happens to stars when they fall into a black hole, how fast can they feed the black hole. But if you add some dissipational process, for example, in our case we're interested in gravitational waves, but it could also be in principle the tidal forcing of the star by the tidal fields of the black hole, or even some interaction with massive accretion disks that drags against the star. Then once you approach a very radial orbit, you reach very close to the center every periapse passage, every time you lose energy, and if you do that fast enough, your star drifts away, it loses energy, it becomes more bound in this direction, faster than it can be scattered by the other stars, so you get locked here. And the details of getting locked into this inspiraling orbit actually determine the eccentricity distribution that you will see once your energy has, your orbit has become so tight that it enters a certain range of interest where the power emitted by your dissipative process becomes very strong, very, very large. Of course, as you go in this direction, the period becomes shorter, so the power, energy per unit time, becomes larger. If you're detecting gravitational waves, both the power and the frequency may enter your detection band, and there is a fairly short-lived phase here where you can actually emit detectable gravitational waves. Okay, and the orbital properties that the star has, statistically speaking, in this region are determined here at the transition phase between the scattering-dominated part of this random walk in phase space and the deterministic, dissipationally dominated trajectory over here. Now, it turns out that if you average over all initial angular momenta of the star, again, we're talking here about statistics, you find there is some critical energy, or if you want to think about it in a more tangible way, there is some typical distance from the black hole, where if you start out your process beyond this distance, you will always do this kind of thing faster than this kind of thing, and you will plunge. And statistically speaking, if you start out here, you will actually always be caught into the inspiral orbit rather than plunging it. And so to first order, to estimate the Emery rate, what you need to know is how many stars you have within this critical radius, and divide it by the dominant relaxation process inside this radius, and this gives you the Emery rate. Now the subtlety here is that the critical radius itself depends on the relaxation time. So this is not necessarily a very trivial thing to solve. And the other subtlety is that you do have to identify what is the dominant relaxational mechanism. And as I already said, these could in fact be quite a few such mechanisms, and they all compete. Okay, so this was the introduction. Now a few words about resonant relaxation. This is the nth time I'm showing this slide, so I will be brief. There is some new results I'd like to discuss. So just to remind you, we're talking here, the name Resonant here is actually, I find it not a very good name. I think the resonance people, or that was in Ralph Intermain's mind when they coined this name, was the resonance on a Keplerian orbit between the radial and azimuthal periods, but a better name I would say would be coherent and relaxation. So if you have a potential that has some high degree of symmetry, it actually restricts the unperturbed orbits, and they have constants of motion, which means that when you look at the effect these orbits have on some test star, because they are not completely random, the kicks the test star will be receiving are also not completely random, and they do not add in the slowest way possible, which is just by the square root of the squares, so in a random walk fashion, but they can add up coherently. And so, for example, if you have a Kepler potential, your orbits are fixed ellipses, and these fixed ellipses will exert a constant residual torque because you have a finite number of stars, and even though the stars are distributed randomly, when you add up the torques, each of them applies on a test star, the torque is not identically zero, but there is some residual small residual. And this is known as scalar resonant relaxation, and the name scalar comes because this can take a star on some elliptical orbit and change both the inclination of the orbital plane and also the size of the angular momentum, and in principle it could take a fairly circular orbit which does not approach the black hole very closely and make it into a very radial orbit that does approach the black hole very closely. So in principle a star that had no chance of becoming an Emery could become an Emery by this very fast relaxation mechanism. If the potential is just spherical but not necessarily that of a point mass, the orbits are fixed on the orbits lie on fixed planes. If you average over time the rosettes that they make, you can think of their masses smeared over these annuli. The annuli then exert the net torque, but by reasons of symmetry, the torque does not change the magnitude of the angular momentum, but it does change the orientation. So this is less relevant for Emerys, but it is a much more efficient mechanism than the scalar resonant relaxation, and so as I'm going to try and convince you, this effect is actually already may have observational consequences that are within reach today. Now, this is an idealized picture because here the potential is assumed to be perfect, the symmetry is assumed to be perfect. In practice, it can never be perfect, even for the reason that, for example, here, resonant relaxation itself is torquing all stars. My description of the system as schematically being divided into torquing stars and a test star is just a pedagogical artifice. In fact, all stars are torqued. And then In other cases, there could be mechanisms like precession due to the enclosed mass, so deviations from a Kepler potential, or even if you're close enough to the black hole, simple GR precession, which destroy on long time scales this perfect symmetry. And so after a certain time, the symmetry is destroyed, the coherence is destroyed, and the evolution of the angular momentum becomes a random walk, but it is a random walk with a very large step size. So the contribution of the resonant relaxation, if you want to make an analogy, say, to the diffusion of a photon through a stellar atmosphere, you have two issues. You have the scattering length, and even though, sorry, put it this way, if you have a very short scattering length, a coherent length, where the change in distance is linear with time, then scattering overall takes a long time for the photon to diffuse from the center out. But if you can somehow increase the mean free path, then you'll have to have less steps before you reach the outer atmosphere. This is what resonant relaxation does on long time scales. It increases the mean free path in phase space. Now, there are now several concurrent attempts to actually quantify the many different parameters that enter into this process in order to go from the qualitative level of description to an actual quantitative level. So this is just one example of n-body simulations, full n-body, no tricks, no attempt to model resonant relaxation by effective mass wires and mass disks or so on. So this is the easy but slow and hard way of doing it, and we're making slow progress in it. What you see here are the change in angular momentum and in energy. The red line is energy, and the energy goes as square root, as expected. And the angular momentum displays a very non-trivial behavior at a very short time scale. We find that actually non-resonant relaxation dominates, but then if you wait long enough, the change becomes linear. And from these curves, you can actually measure the efficiency of resonant relaxation and also test things like how does it depend on the actual structure of the nucleus? Does it behave differently when the cusp is steep or when the cusp is shallow? All of these things are not really well understood at this time. Our preliminary results imply that, in fact, at least according to our simulations, the predicted rate of MBHs is somewhat decreased compared to what would be implied by the original results by Rauch and Tremaine from about a dozen years ago. And this is expressed on this plot. So very briefly, what you see here is the rates of, so this is inspiral events and plunge events. And the rate is normalized to what you would have in a world where resonant relaxation does not exist. So when you go, and this is some measure of the efficiency of resonant relaxation, which in principle is one of the numbers that we're trying to get from the numeric simulation. So if you go all the way to the left here, this is when you have absolutely no resonant relaxation, and then of course these two lines, by definition, should go to 1. As you increase resonant relaxation, initially, because it helps orbits go from circular to radial, the inspiral rate increases, but then it becomes over-efficient and it actually throws everything into the black hole rapidly, and you get this very steep exponential, or I think it's even stronger than exponential, cut, and what you have instead are plunges. That's the blue line. Now, Rauch and Tremaine derived a number which, by pure coincidence, turns out to be roughly very close to the peak amplification of MBHs. Here, this scale is normalized compared to their value. We find with our simulations that, in fact, it's somewhat lower. As I said, the simulations are difficult. Since we're taking the hard route of doing full n-body, it's very hard for us to extend the simulations over a very long time scales, and there are various subtleties that I don't want to get into here that could argue that this is definitely not the last word on the subject, but at least you can see the direction that things are going. We are trying very hard to verify whether we are on this relatively safe side of the curve or somewhere on this very dangerous side of the curve, okay? And their final results are not yet in.
And do you have a sense of how much scatter there is in these efficiencies? And I'm talking about scatter not scatter per given nucleus. The scatter will not increase as you do more simulation. One nucleus happens to be.
Yeah, sure. You're talking about the scatter, not the error on the mean, but actually the RMS. Yes, I believe it was rather large, a few tenths%, but I have the numbers in the preprint. We can look at them.
So I don't understand what the horizontal scale is.
The horizontal scale. So there are various numeric prefactors, or at least we hope that they're just numeric prefactors and not functional prefactors that go into the rough order of magnitude estimates of resonant relaxation. Now we want to actually pin down these numbers, and you do the simulations. Now there are many different ways to express these quantities. I chose here to express them by some ratio. There's a reason why this appears in the square, etc. I won't get into it, but the basic idea is that Rapp and Tremaine, for example, parameterize one of these parameters they call beta S, and they get some value. Now we get another value. And so this chi, which is related to the efficiency, is normalized to be 1. If we would have gotten the same value as they did, it's 1. We're getting a somewhat larger value, and this then takes you from this side of the peak to that side of the peak. So that at this level of change, it's not a big deal. But the question is, will it take us here? Then we'll be unhappy. Okay. Yeah.
How resonant relaxation depends on the density?
The scalar does not depend on the density. Scalar resonant relaxation has the remarkable property that it depends only on the mass ratio between the black hole and the typical star. The vector has a weak square root dependence on the number. But the vector is probably less relevant for the question of embrys, luckily, because it's an extremely efficient process, as I'll argue in a second. So simulations are definitely one way to try and study this problem. Do we have any observational links that we can actually test these assumptions? And one promising but definitely hard to interpret case is the Galactic Center. And so what you see here is a plot of, well, first of all, this is a typical distances parameterized by the semi-major axis of orbits from the Galactic Center across basically almost the entire radius of influence. And here is time scale in mega years. And overplotted on this plane are different populations of stars that are actually observed or are noticeably absent in the Galactic Center. And there are many different populations of stars. We can date them by their knowing stellar theory. And for example, these are the relaxed giant stars. They tend to be older. They lie here at distances further from the center, and they are older, so they extend on the top. There's also this cluster of, which I'll come back to several times in this talk, of very young and rather mysterious stars called the S stars, which lie very close to the black hole. We're talking here about distances of a few hundreds of parsec. And one of the most intriguing and I think the most dramatic discoveries of the last few years is what are star disks, or at least there's at least one disk that is stars that are very young, very massive, and moving in disk-like orbit with a very well-defined sense of revolution. And they appear to have a very clear-cut inner edge. And when you plot, and this is a naive plot in the sense that there are many ingredients in this calculation of relaxation times here as function of distance that we have been knowingly omitting because the problem is rather difficult as it is. So if you, for example, plot the vector resonant relaxation time, which would, to remind you, take a disk, stars moving on a disk, and randomize their orientation. So it will basically disrupt the disk-like structure. It will not look like disk-like anymore. you find that it falls, the age of the star disk, those stars, equals the predicted vector resonant relaxation time scale at the inner edge. So this is where you would expect resonant relaxation to be efficient enough to disrupt the disk. And in fact, these stars here are missing. There are no stars. And now there is a big controversy whether these S stars are in fact the lost inner extension of the original disk that was randomized. I don't think that's the preferred explanation for other reasons which I won't get into now. But the S stars are indeed, in principle, at least some of them, the longer-lived ones and the ones that are closer to the center, are susceptible to scalar resonant relaxation. So here are two curves which we believe bracket the realistic value of resonant relaxation. Again, the ingredient missing here is mass segregation, which we will talk a bit in the end probably. So we don't really know where we stand here, but it's quite possible that resonant relaxation actually plays a role in randomizing the orbits of stars, which means that, well, I won't jump forward at this point. I'll just say that this may enter the story of how the S stars are brought to the center. We'll talk about it later. Now, the relaxed giants are old stars by comparison to the S stars, but people tend to overlook the fact that they're not that old compared to the relaxation time, the normal relaxation or non-resonant relaxation time, which is up here. Now, the relaxed giants are observed to be dynamically relaxed. They don't have a preferred sense of motion. They seem to have a very Maxwellian kind of velocity distribution. And in fact, you wouldn't expect that to be the case, given the fact that the non-resonant relaxation time is already approaching, if it's a few giga years old, and it's approaching at the edge of the cluster, almost the age of the universe. And it could well be that the reason that these guys are relaxed is because of that vector resonant relaxation definitely would have destroyed any coherent motion, and even scalar resonant relaxation can affect them. And on these scales of a few tenths of a parsec, resonant relaxation indeed can do various things. And this is a newer result that I'd like to show. It's from work in progress with my student, Michael Bregman. And in our attempt to find physical systems where resonant relaxation is at work and where we can test our ideas about it, we came up with the idea that perhaps maser disk warps are explainable by resonant relaxation. And we're getting very encouraging first results. So this is the famous maser in NGC 4258, and it's observed to be warped. And when people try to reconstruct the structure, so this is where the black hole is thought to be, the 4 times 10 to the 7 solar mass black hole. This is some radio jet, a small jet being ejected from it, and these are the major spots seen obviously in an almost edge-on disk. That's why we see the maser. And you can see this is a reconstruction, but you don't need the reconstruction to see by eye that you have this sigmoid kind of curve right here. And in fact, there are various ideas how to make these warps, and none of them is, in my mind, terribly compelling, although they could well work. One of them, by the way, which is of interest to this audience, is that this is the outcome of the lens steering precession, interaction between the disk viscosity on one side and the torques of the lens steering precession on the other. But this system, we are almost sure, we're certain in fact, that it's embedded in a very dense stellar system if we take the M sigma relation seriously. And the different stars around it, in which it is embedded, will be exerting torques, vector resonant relaxation torques, on this very slowly moving, almost Kemplerian system of circular gas streams. And in fact, you need very few stars to do that. So here is one very rather abstract simulation of just 4 or 5 stars, 5 stars, on the very inner part of the disk. So this is not this disk, but actually it tries to simulate in some very toy model fashion the inner part of a luminous accretion disk. And even if you, very close to the black hole, even with the mass segregation, you don't expect to have many black holes, stellar black holes around. But a few are enough over some time to take this initially ordered stream of gas represented here by discrete mass points and warp it, not only tilt it, but also introduce some kind of something that looks like a wave pattern in it. So one intriguing question for the future would be that maybe resonant relaxation not only affects the dynamics in a massive black hole, but also could affect the evolution of the black hole, because if you start torquing the disk, you're transferring angular momentum from the stars to the disk, you're changing the spin evolution of the black hole. Spin evolution, a different spin would change the radiative efficiency. By changing the radiative efficiency, you can, of course, affect the luminosity of AGN, but you also affect the, how hard or difficult it is for mass to flow into the black hole, so you affect the black hole evolution rate. So, in principle, one could imagine, if nature chooses to be interesting, that we can actually tie in the evolution of black hole and cosmological timescales with resonant relaxation. But that's still something that we have to check, because it's quite hard to get strong enough torques very close to the black hole. But going back to this simulation just shows you that the effect works as predicted. There's nothing special about torquing rings of gas by stars. Going back to the maser, this is a very complicated plot, which I don't think you will learn much by studying every line. I'll just tell you the story that this plot is telling. Okay, so the story, this is a distance scale from the center. And the red zone is the red that is efficiently torqued by the stars. And the green zone expresses the spatial range between the inner and outer edge of the disk. And the fact that the green zone lies within the red line tells you that anywhere on this scale, between a few hundredths of a parsec up to half a parsec, and even further out, resonant relaxation by the cusp of stars that we expect to be there can easily torque over the lifetime of the disk, taking into account that it's flowing in. So you have to torque the gas faster than it flows in, otherwise it will not be there on a stable, fixed orbit to coherently absorb the torque. And you also have to take into account that you need enough residual angular momentum in the stellar system to transfer to the disk. And all these conditions, which are rather stringent, are easily satisfied here. So what you see is that you can actually do a 10 degree warp in the disk by about the billion star or so that lie on this scale around the maser disk. So if you believe this model, then we are observing the effects of resonant relaxation in such disks, and maybe this will open a channel to further testing the resonant relaxation mechanism. Okay, so I've spent a whole lot of time on this, so let me just go fast about massive perturbers. So the basic, if you remember, we started when I introduced the relaxation time scale, I mentioned that the relaxation rate scales like the product of the density and the mass squared. And this means that even if we have some very massive objects in the system, even though their density may be very low compared to that of stars, if the m squared factor wins, then you can easily have fast relaxation by these few objects, much faster than you would if the system were composed solely of stars. And in fact, turns out that if you look at what we actually see in our galaxy, which is a prototypical gas-rich spiral, you find that giant molecular clouds, which have a mass range between 10 to the 4 to 10 to the 7 solar masses, and there are some 100 such clusters within about 100 parsec, accelerate relaxation by many orders of magnitude compared to what you get from the stars alone. And this, in fact, is not a new idea. It was already brought up by Spitzer and Schwarzschild in the 1950s to explain why the galactic disk is more puffed up than it should be. And people have even started suggesting that it may lead to a higher rate of delivery of stars to the central black hole. But it turns out that when you actually study this in more detail, that in fact these massive perturbers, because none of them is very close to the black hole, are not that great for accelerating the rate of throwing single stars into orbits that come very, very close to the black hole, but they're very efficient in accelerating processes where you don't need, for something interesting to happen, you don't need to be very close to the black hole, you can be somewhat further away. And things where this is interesting, there are two examples that I'll give, and one of them is if you want to disrupt a binary, because then the relevant size scale that you're disrupting is not the size of the individual star, but the binary separation, the semi-major axis. And also, it's relevant for the problem of accelerating the mergers of massive black hole. So the interesting thing here, I'll be brief about this, I guess Melvin will talk about this more, is that when you disrupt a binary, you actually get a mapping between the semi-major axis of the binary reservoir far from the black hole and the semi-major axis of the captured stars. So here is a schematic depiction of the binary disruption. You capture the blue star and you send off the red star as a hypervelocity star. And if you start out with this distribution of periods for the binaries, and the periods, even if all binaries are born, say, with this kind of a bimodal, that's what people think happens for a white dwarf binaries, bimodal distribution, depending on where they come from, this initial distribution gets modified by interactions with field stars and by the fact that the very tight binaries actually decay by gravitational wave emission well before they are thrown to the black hole. And you map this, whatever distribution you have, you map into a distribution of distances from the center. And the mapping is a statistical nature, but this tells you that whatever you see, the stars you see orbiting around the black hole and the stars you see thrown away as hypervelocity stars encode in them information about the parent binaries. Now, in fact, we think that the S stars we are seeing today have in fact been captured by that mechanism. The S stars are known observationally to be absolutely and totally normal stars. There is no indication of anything special about them, even though they orbit, some of them, within a few tens of an hours, light hours from the black hole. That's very strange. They also have a mass function, which is very normal. That is, the number of stars per unit mass is very similar to what you see far away from the black hole, and it's quite unsimilar to what you see in the stellar disks that lie around the black hole. So there are many different indications that the S stars are normal stars that were formed far from the black hole. If you then map how many stars you expect to see, given if the rate at which these binaries are thrown at the black hole is determined by the very efficient process of perturbations by massive perturbers, you find that you expect to see anywhere, say, up to a few tens of such stars, and you see about 10 to 30. This is the cumulative number of S stars, this function of distance, and these are different models for the massive perturbers. The probable truth lies between this red and magenta line. So the numbers sit together very comfortably. It's a consistency check, it's not the proof. And the same can be said about the number of observed hypervelocity stars. We predict here 10 to 50. We see of the same order. These numbers are not completely up to date, but the big picture doesn't change. This idea is consistent with what both the S stars and the hypervelocity stars. It would probably increase the rate of white dwarf MBHs, and there is a question which we're still studying whether or not this actually would increase the incidence of low eccentricity MBHs. Our latest result is that it increases it, but not very significantly. That the total rate, I believe that's correct, right, Clovis? Because the numbers were changing a bit over time. But I believe that our latest, still unpublished result is that the total rate will be dominated by high eccentricity MBHs, but that's not final. And very briefly, if we have a case of a stalled binary black hole merger, then massive perturbers will throw single stars this time from far away through the sort of aperture, if you want, through the orbit of the black hole binary, and this is efficient enough to accelerate the decay and have it happen within the Hubble time for almost all range of binary massive black hole masses, and for almost all kinds of types of galaxies. With stars, this is completely hopeless, and this result has been known for a long time, that if you have a spherical system with no gas and only stars, the binary stalls. But if you add this extra boost by massive perturbers, apparently only very massive gas-poor galaxies may still be hanging there without coalescing. So this is again good news for Lisa. Now, this is some aside, but it's interesting for GR. This very same binary capture process, which up to now I discussed in the context of the S stars. So the S stars are relatively massive and relatively young and bright stars, but the massive perturber mechanism has no special preference for massive stars. All binaries will be thrown towards the black hole, including low mass binaries like 1 solar mass, half solar mass. And these tend to be much tighter, and they can be easily captured very, very close to the black hole. And in fact, directly populate highly relativistic orbits. And there was very recently an interesting paper by Cliff Will, which speculated that if there were stars on orbits that of 1 year, or maybe anywhere between 10 years and less, around a black hole in our galactic center, we will be able to, using more than one such star, if we were lucky enough to actually even test the no-hair theorem, essentially by measuring independently the precession rate due to the Schwarzschild term, the spin term, and the quadrupole term. Now, initially I had reservations about this idea because we know today that we see absolutely no stars with periods less than about 20 years. And if you hope that you would be able to see these stars by looking deeper with future generation of telescopes, then you have to explain why these stars actually survive in this system, which we know today is probably dominated by stellar black holes that will destroy very rapidly any star that lives there. And as far as I can think of, the only mechanism that could repopulate these orbits is capture of binary, the tidal disruption of binary stars that are sent at a high enough rate by massive perturbers. And so what you see here is a scattering experiment. So let me briefly explain what we see. I think the reason I'm showing it here is because I believe Clovis talked about gravitational wave flashes or bursts from the galactic center. Now, this is a question I'm throwing to the audience. So imagine that we had information coming from stellar relativistic orbits, which would tell us something, say, about the spin of the black hole, even the direction of the spin of the black hole. And then we had another channel of information coming, say, from gravitational wave bursts. Is there anything new and better that we can do than by using just the gravitational wave information alone? This, I think, is something that we should consider. It's still speculative, but, I mean, it could well happen. So going back to the plot, what are actually we seeing here? So this is period, or if you want, energy or semi-major axis. And this is 1 minus the eccentricity of the orbit on a logarithmic scale. So stars here are very, very radial. And this is just a re-imaging, in the sense of the plot that Cliff Will showed in his paper. These contours predict how much would be the astrometric change in the orbital parameters per year for, I think this is a black hole that spins at 0.7 of the maximal spin. Again, this is just an assumption. And so you can see that if you have, the rate of the precession increases as you go to shorter periods, that is, you're closer to the black hole, you're deeper in the relativistic regime, and of course, as you go to more and more eccentric orbits. The green are the Schwarzschild precession, the blue are the spin precession, and the red are the quadrupole precession. Now this, it's not very clear here, this is, what you see here on this plot are the results of Monte Carlo scattering experiments. So first of all, you assume that the binary was disrupted, leaving one star orbiting very close to the black hole, which is represented by these dots. The distribution here maps some assumed distribution of the parent population, and there is some scatter in this and this directions because all these statements about the mapping are statistical statements. And then you plug in the various processes that we discussed: normal relaxation, resonant relaxation, gravitational wave emission. You have some naive model for the tidal energy dissipation, and you include collisions, destructive collision with a very steep cusp of stellar black holes. And you just run this, and you ask yourself, what is happening to the period and eccentricity of the star, and at which point is it destroyed? And so if you play this game long enough, you can, first of all, see what are the branching ratios, what is the final outcome. No star survives in this environment more than a few 10 to the 7 years, or maybe 100 million years. And then once they're all destroyed, you can see that most of them actually die by being tidally heated to the point where they either evaporate or puff up to the extent that they are disrupted. This is a curious and amusing phenomenon in itself that we call squeezars, because for a short while these stars can be extremely luminous. And we anticipate that lower luminosity squeezars will be produced at the rate of about such a rate that at any given time there will be maybe one such on a very close orbit. They are still undetectable by today's technology, but they could be detectable in the next few years. So that's one way of testing this idea.
How
Yeah.
do squeezars which evaporate go through a supernova and leave a black hole remnant?
I don't think so. No, I think they simply evaporate because they're heated through the bulk by the tidal dissipation. So it's not associated with the compression. So I don't think there should be a supernova. These are sorry, I didn't mention. This is for solar mass stars that belong to two solar mass binaries. You could, of course, include some more realistic mass distributions, etc. This is just the first attempt. The others are disrupted because they are caught. At the moment that they are captured, they're already on a very radial orbit that leads them to the tidal disruption radius, and about 8% are destroyed by collisions with the stellar black holes. But this is what ultimately happens to them. But before they do that, you can ask yourself, after, say, a shorter time scale, after 10 to the 7 years, where will these stars be on this plane? And this is depicted by the black dots. I believe it's here after 10 to the 7 years, right? So you can see this is slightly misleading. We don't expect to have that many stars around the black hole. This is just, if you can sort of by eye assess where the density of points is strongest or largest, that's where it would be more probable to find the star. And so you can see, I think it's fair to say that without doing this very quantitatively, that somewhere around here, this region appears to contain most of the stars. And you can see that it seems that we can easily get orbits that are deep in the regime where the spin precession is quite substantial. By the way, 10 milliards seconds per year is the anticipated resolution of the next generation VLTI AO-assisted camera or interferometer that's known also as gravity. This is a proposal by the MPE that was, I believe, recently approved. It seems that getting to a very high level of quadrupole precession is rather hopeless with this. You see there are very few stars lying around here near the leftmost red line. But even two stars, or at least I believe two for measurement, three for confirmation, are needed to detect the direction and the spin parameter of the black hole if you have them around here. So maybe that's an information that we can actually, at a certain point in the not too far future, actually obtain. Okay. So I'm well beyond what I planned to my time, so I don't know if we want to talk too much about mass segregation. I guess I'll just leave it to the audience. Are people itching to leave, I won't be offended. Vera, you're the boss, so okay. I'll do it fast, okay? So, first of all, just for completeness, we keep saying that we expect to have cusps around the relaxed stellar systems. Here is the proof why. So, just as a consistent solution, let's assume to start with that we do have a cusp. So the distribution goes like r to the minus s, and this is a case where we have only one type of stars, only one type of mass in the system. The relaxation rate, which we already described, then can be expressed in terms of this s by this relation. And any of these stars carries this amount of orbital energy. And now let's assume that stars are destroyed very close to the black hole, which means essentially that to get so close to the point where they were destroyed, they had to be kicked there by other stars, and therefore they had to give their own orbital energy to some other star. That star then interacts with the many n stars in the system, and eventually this energy has to be carried out in steady state. And so, if the number of stars enclosed within a shell, within a sphere of radius r is 3 to the minus s, then the rate at which this energy is carried out is simply the number of stars times the energy per star divided by the typical time scale, and it scales with r like this. If you assume steady state, the energy flux or energy transmitted energy, actually energy, the power, orbital energy power transmitted out of the system cannot depend on radius, and so this S must be 7/4, and this is the canonical result that also Miguel showed yesterday in many of his simulations. And this is what we expect in a single mass population, and indeed, as we know, it's borne out by experiments. Now, this is the weak mass segregation. Again, I'm just showing it. Essentially, tells you that if you have a distribution of stars, you have this very simple and surprising, in fact, scaling relation between the power law dependence of the density profile and the mass of the star. And so if the low mass stars tend to have PL go to 0, so they go like r to the minus 3/2. This is shown here in Fokker-Planck simulations, and the more massive stars will have the 1/4 solution, which actually is like 7/4. If you think about the density, this is also the solution for the single mass. And we now realize that the fact that Bacalov got this result is because in the older models, the massive stars were so plentiful in the system that they essentially behaved as if they were the only mass in the system. They didn't care about the light stars, and so they simply found themselves or relaxed into the single mass population result. Now, in fact, we had inklings that something was wrong with the Bacalov results way before we actually understood them. And this is we saw it in our own simulations, in Fokker-Planck simulations, where we had systems with what we believe to be realistic mass ratios, where the massive stellar black holes are not that plentiful. And Mark Freitag also saw it in his simulations, which use a very different numerical technique, in the sense that it also includes can include also many other physical processes, and it also has a much more realistic boundary conditions. And so we don't expect to see exactly the same slopes, but we do see slopes like here that far exceeds the 7/4 slope. And the last hint, which is also, I believe, rather problematic, but I think, well, I still have some hopes that it will be borne out one day, is that in fact you can identify in the Galactic Center, if you look at the mass of all of the stars that are observed there, you can actually identify a type of giants that are very low mass and have a very distinct luminosity signature. These are called the red clump or horizontal branch giants, and you can pick them out from the stars just by limiting yourself to that particular luminosity beam. So let me skip this. This is just to show you that they stand in various different criteria of mean mass, number, and fraction. This particular beam, around 15 to 16 K K magnitude is dominated by these low mass stars, and they're much less massive than the typical stars. And if you then plot the spatial distribution, the number counts essentially, or the surface density of stars that are slightly fainter and slightly brighter, than these stars, you see that they have a much flatter distribution than either the fainter or brighter stars, which have higher masses. Now, this degree of flatness is way beyond what you would expect from the Bacall-Wolf solution. And while this interpretation is not unique and it's very problematic, and I'm the first to admit it, it could be actually evidence for strong mass segregation in the Galactic Center. And it's probably the only system where we will ever, in the foreseeable future, ever be able to actually test this. And so, Clovis defined the delta parameter. I won't go into it, but I just want to show you that, in fact, why we believe that this is strong mass segregation could well be more common than actually the weak mass segregation solution in nature. So what you see here is the results from what's known as the stellar population synthesis calculations, where basically you assume some initial mass function. So this is mass, and this is a number per unit mass, and this is what's known as the universal initial mass function, which it's called universal because people believe that this actually is what, for some unknown reason, nature chooses to produce in a huge variety of conditions. It's an empirically motivated mass function. And then you let that mass function evolve, and you can give it various prescriptions. For example, one prescription would be to just stop star formation at t equals 0 and then see what happens when the stars evolve passively. These are known as coeval systems. Or you could do what apparently is happening in the Galactic Center, that is to allow new stars to be formed at some continuous rate over the history of the galaxy. And in both cases, if you wait long enough, and long enough here is 10 gigayears, what you find is that this magenta mass function morphs into a mass function which has two distinct mass peaks. One is constant in this region, so it's 1.5 or so stellar masses and lower. It's composed of all the low mass main sequence stars that are basically have a very long lifespan and can survive more than the Hubble time, as well as all the low mass stellar remnants, so neutron stars and different types of white dwarfs. They're here represented for simplicity as delta functions. There must be some kind of a distribution, so in real life we will probably have some big hump around this range. It won't be a superposition of delta functions. And more speculatively, we expect that all the stellar black holes will be well away at the 10 solar mass range or so. Again, here we also expect some distribution, but the peak, I think, is that universally agreed that the peak of this, whatever is the mass function for stellar black holes, is well away from 1.5 solar masses of neutron stars. And so this happens whether we allow continuous star formation or we let the system evolve passively. The system, if you want, polarizes, so to speak, into two mass bins. The 1 solar mass bin and the 10 solar mass bin, which is very easy to model. And so, by the way, you can see that it starts out with delta above 1 and it ends up with delta less than 0.1. And in fact, if you ask yourself, if we had a pure power law initial mass function, what would be the break-even point where delta after 10 gigayears is exactly 1, and that turns out to be with this slope. So it's the canonical salpeter power law, which is the power law approximation of these universal mass functions, has minus 2.35. So if you just went by the canonical salpeter, you would come to the conclusion that all stellar populations evolve after time into a delta less than 1 systems. And this, you've seen this yesterday for, I think, more than once. Well, maybe Miguel showed the low resolution image. And so here you see delta for 2 mass population, you see delta, and you see for different mass ratios in between M heavy over M light, And you can see how the slope, so here, this point here, is for a single mass, that this is the R goes like -7 quarters. Anything beyond that is something that lies outside of the domain of the weak segregation. Now, funnily enough, Packard and Wolf did everything correct, but then they chose to test their models for specific realizations, and these are the white circles here. All their models were concentrated on this branch. That is why they reached the erroneous conclusion that their solution is universal. They consider this to be a very generous spread of possible models, and they saw that the differences were tiny, and they reached the conclusions that weak segregation, they didn't call it that way, is the universal solution in the relaxed system. But we simply, well, it's not so simple in detail, but conceptually it's simple, we simply extended this grid, in particular to the point where, to the delta value, which we think, for example, the Galactic Center may have. And we find that it's much steeper. So, I think it's fair to say that although we don't understand mass star formation very close to galactic nuclei, there is a very substantial possibility that in fact it does lie in the strong segregation regime. The implications for MRIs are non-trivial. We had a short discussion yesterday. I'll just remind you that these are systems which have less stellar black holes per unit stellar mass to start with, but they take those fewer stellar masses, stellar black hole masses, and squeeze them closer to the black hole. Do you actually end up with more or less? Depends on how you want to compare. Do you compare two systems with the same stellar mass, two systems with the same stellar black hole mass, same total mass in the radius of influence, and so on? I think that it depends somewhat on how you ask the question. I don't even know what actually Laban O'Leary did offhand. What was their? You mentioned yesterday, Clovis, that they compared two models, but in what sense were these models the same, and in what were they different? I mean, how did they normalize? I don't know. So, well, maybe it's not even really relevant to speculate on what they did, because
well, they did is one model was very similar to ours. One model they had.
But it would.
10 times more.
But they rescaled the entire mass of the stars there. Why did they keep the same when they compared these two models? I mean, when you compare two things, you fix some parameters and you change only.
The density of main sequence stars is the same.
They kept the total density.
The density of
Main sequence. I see. So it has more stars, more stellar mass than the other one. Okay, I don't know if that's actually meaningful. What I'm saying is simply, it could be very simple to make this a meaningful comparison. I didn't get yet to thinking about how to do it correctly. What is the relevant question when you want to compare two universes? If we live in a universe with weak segregation, what would be the ME rate? And then we live in an alternative universe where everything is strong segregation, what would be the ME rate? I'm not sure that I know offhand to tell you how to do the comparison. I think, though, that we all have the tools to do that. Okay. So this is my summary slide. Again, I want to emphasize that we do have here really two linked challenges. They're both interesting in their own right. And that I'm really very enthusiastic about the future prospects of gravitational wave astronomy to tell us what's happening near black holes. I think there's a lot of important input that we can get. I emphasize that we should always remember that at this time we are looking at a very special subset of all galactic nuclei, at least as far as we believe the extension of the M sigma relation to lower masses, and that it appears we can easily identify several fast relaxation processes that actually dominate the dynamics, and this is a new result of the past few years. Two-body relaxation is definitely not necessarily the important player there. I already suggested two tests for our ideas. One are observations of the Galactic Center. The other newer result is maser disks, maybe telling us something about resonant relaxation as well. And the question that I'm throwing is an open question, and I already alluded to it when I talked about the torquing of disks by resonant relaxation, is that we could actually affect the accretion processes. These fast relaxation processes could affect the accretion processes and therefore affect the cosmological evolution of black holes. This is something that was not really, I think, discussed or even digested in any way, and could open a very new, an interesting line of inquiry. So I guess I'll stop here. Thank you.